Okay, want to quickly finish chapter 19. It was fun seeing the unsafe Rust code. So we gotta look at all the advanced features and then put the book on the shelf. Well, we still have a final project, but we can put the book on the shelf and then come back to it when we need to. But let's move on to finish reading of them first. And yeah, I don't know how long it will take for the final project, but we'll see. I don't know if I have time to finish them before I go to Berlin, so maybe tonight later, I don't know. I still have stuff that I have to do. Advanced trades. So first, this is what we normally do with trades. This is the public one. So give me all the details about trades. Placeholder type. Associate type connect a type placeholder with a trade which such that the trade method definition can use these placeholder type in their signatures. The implementer of a trade will specify the concrete type to be used instead of the... Oh, 1 second. Sorry about that. 1 sec. Yeah, I just realized I forgot to minimize my chat, so immediately close it. Okay, so specifying placeholder types in trade definition. Right, so I think it's easier if we see an example. How to... So we have an item. Okay, so we're using it here. That's why we would have to have the associate types. Without needing to know exactly what is this type until this trait is implemented. Associate types are somewhere in the middle, used more rarely than feature explained in the rest of the book, but more commonly used in many other features used in this discussed in this chapter. Yeah, so iterated trade, we have the associate type items. So the type item is a placeholder, so we don't know what is item actually, because it depends on what is iterated, right? So the next method's definition show that it return the value of the type self item. So the implementer of iterated trade will specify the concrete type. So for example, I'm impelled iterator for the counter, and then the type item will be U32. So I have to do it like that. Yeah, why we don't use generic like that? The difference is what when used generics, we must annotate the type initial implementation. We can also implement iterator string for counter, other type. We could have multiple implementation of iterator for counter. When a trait has a generic parameter, it can be implemented for multiple times. So now we can have different changing the concrete types of generic type parameter each time. We use next method on counter would have to provide the type annotation to indicate which implementation of iter we want to use. So that is too generic, I think, using generic type. So we want to make sure that for counter there's only one type, that is the item type that has been used. For next, associate type, we don't need to annotate type because we can't implement a trait on a type multiple times. With the definition that use associate type, we can only choose what type of item will be once. So once you have chosen the item type, you can't change it for something else. So you can have multiple ones. Only be one impel iterator for counter. Yeah, if we do it like that, then we can have multiple iterators with different types. Yeah, we don't have to specify that we want an iterator of U32 values everywhere when we connect. Associated type will also become part of. Oh, sorry, I've been so tired recently. I think EuroPython really drained all my battery, and now I'm slowly charging my battery back up. But we're almost finished the book, which is a good thing. So associate type also become part of the traits contract. So implementer of the trait must provide type to stand in for the associate type placeholder. Associate type often have a name that describe how the type will be used. Documenting the associate type in the API documentation is a good practice. So it's part of when you implement the trait, then it's part of the design that you have to set what type it is. Default generic types, parameters, and operator overloading. When we use generic type parameters, we can specify the default concrete type for the generic types. This eliminates the need for the implementer of the trait to specify a concrete type if the default type works. You specify a default type when declaring a generic type with placeholder type equals to concrete type syntax. So what is that? So we have point, which the plus operator. Ooh, okay. A great example of a situation where the technique is useful is with operator overloading, in which you can customize the behavior of an operator in particular situations. Rust doesn't allow you to create your own operator or overload arbitrary operators, but you can overload operations and corresponding trait listed in standard ops by implementing the traits associated with the operators. For example, we overloaded the plus operator to add 2 points instance together. We do this by implementing the add traits on a point struct. So technically you can't overload, but because the trait you can implement it yourself, so you can do that. So we have points, we will have other derive the other struct, other traits, but then we will implement add for ourselves. So debug, we will use it here. Partial echo will probably also need to be used here. Copy and clone as well. But add, we will have the type output will be the point. So add will take a point. So it will be added to itself, x and y. Then we'll give out another point like that. So here we have outputs equal to point here. Here is still item, but I think here you can. Why is it not self output here? Oh no, yeah, because it will be a point. Yeah, it'll be a point, but why? Okay. Yeah, you can just self output, no? So here we have. So you can add 2 points together. You can assert these two are the equal. Add methods at x and then add y. The generic type in this code is within add trait. So the add trait looks like this. Right hand side equals to self so it can only add to the same type as self, I guess. Type is, so output is the associated type, I think. For overloading, so this is, yeah, right hand side, self is self. This code should look generally familiar, a trait with one method and associate type. The new part is right hand side equals to self. This syntax is called default type parameters. The right hand side generic type parameters, so it's the right hand side define the type of the right hand side parameter in the add method. If we don't specify a concrete type for the right hand side when we implemented the add trait, the type of right hand side will default to self, which will be the type. So that's why here we don't have to say right hand side, because it will be self. Which will be, yep. When we implement add for point, we use the default for right hand side because we want to add 2 points instant. Let's look at an example of implementing an add trait where we want to customize right hand side type rather than using a default. We have millimeters and meters. Holding value in different units. Thin wrapping of existing type in another struct is known as new type pattern. You want to add values in millimeters to using new type pattern to implement external traits on external types. What's this? So it's a new trait. So for example, now we have millimeters, we have meters, add meters for millimeters. So this time right hand side is meters, right? So output will be in millimeters. So it's like this. Add millimeters and meters we specified. Set the value of right hand side type to be parameters instead of using selves. You can use default type parameters in 2 main ways: to extend a type without breaking existing code, to allow customization in specific case most users will need. Standard libraries add traits is an example. Usually we add to like types, but add trait provide the ability to customize beyond that using a default type parameters. In add traits, the definition means that you don't have to specify extra parameters most of the time. In other words, a bit of implementation boilerplate. You want to add a new type, add a type parameter to the existing trait. You can give it a default or allow extension of the functionality. So now you can have 2 add. So you can have millimeters add millimeters, which is the default. But then if you add millimeter with meter, then you have another one. This time we'll multiply it by 1000 because it's meter. Yeah. So it's kind of like overloading, but we use trait to do it. Fully qualified syntax for this ambiguation, calling methods with the same name. So, whoa. Nothing in Rust prevents a trait from having a method with the same name as another trait's method, nor does Rust prevent you from implementing both traits on one type. It's also possible to implement a method directly on the type with the same name as method from the trait. So, name crashing, I guess. Implement a method directly on the type. So yeah, we have all of them as the same name. Was possibly what can possibly go wrong? When calling methods with the same name, you need to tell Rust which one you want to use. Consider the code here. So pilot can fly, wizard can fly. abstract human. So pilot for human, fly will be this is your captain speaking. Wizard for human will be up. Human fly will be waving arms furiously. Okay. Right. So they're all fly. So which one are we calling? So person equals to human, human dot fly. So it's a bit ambiguous. What should we do? So by default, run this code will print waving arms furiously, showing that Rust call fly method implemented on human directly. To call fly method from either the pilot trait or the wizard trait, we need to use more explicit syntax to specify which fly method we mean. So for example, if we want to do that, we have to do pilot, fly, and person. So we can't use person.fly. We have to use pilot, fly, and then end person there. Well, I guess you have to use end person because you don't want to pass person inside and it will be gone. So you could also write human, fly, and person, which is equivalent. A bit longer to write. So now it will be your captain speaking up and waving arms furiously. Because fly method takes a self parameter, we have two types that both implement one trait. Rust could figure out which implementation of trait to use based on the type of cell. However, associate functions that are not methods don't have a self parameter. So they don't have a self parameter when there are multiple types of traits that define on method function. With the same function name, Rust doesn't always know which type you mean unless you use fully qualified syntax. Create a trait for an animal shelter that wants to name all babies dog Spot. We mix an animal trait with an associated non-method function baby name. The animal trait is implemented for the struct dogs, on which will provide associated non-method function baby name directly. So we have struct dog. In dog we have baby name Spot, but animal for dogs baby name will be puppy. So baby dog is called. So if we do dog : baby name, I think that will be a that would be calling this one, right? With Spot. We implement the code for naming all puppy Spot in baby name associate function. The dog type also implement the trait animal, which describe but what do we want? This is not what we want. We want to call the baby name function that is part of the animal traits that we want to implement on dog. So the code print a baby dog is called a puppy. The technique of specifying trait names that we use doesn't help here. So we have to use animal baby name here. Because animal baby name doesn't have a self parameter. So yeah, here we have the self, right? But now here this doesn't have a self. So when we do this, Rust can't figure out which implementation we want. You'll get this compiler error. Yeah, so we need a self. this ambiguous and tells us that we want to use the implementation of animal for dogs as opposed to implementation of animal for other type. We have to use fully qualified syntax. Whoa. Okay, dog as animal. So we have to put both here. Dog as animal baby names. Okay, we are providing a rest with a type annotation with the angle from a bracket. We call the baby name method from animal trait as implemented on dog. So now it's super clear. Fully qualified syntax is defined as this. Yeah. Associate function that owns methods, there would not be a receiver. There would only be the list of other arguments. You could use fully qualified syntax everywhere that your core functions or methods. However, you're not allowed to omit any part of this syntax. Yeah, so you don't need to have receiver if method, which would be self. You could have all these different things. Okay, there are multiple ways of doing things. Using super traits to require one trait's functionality within another is now getting more and more complicated. This is at the territory that like we are doing things that normally you won't do. So what are we doing here? You may write a trait definitions that depends on another trait for a type to implement the first trait. You want to require that type to also implement the second trait. You will do this so that your trait definition can make use of the associated item of the second trait. Your trait definition is relying on its core super trait of your trait. For example, let's say that we want to make a outline print trait with an outline print method that will print a given value formatted, so the frame in asterisks. This that is given a point abstract that implements the standard library traits display to result in x and y. 1 for x and 3 for y. So this is okay. Do we need a point to do that? In the implementation of outline print method, we want to use the display trait functionality. Therefore, we need to specify that outline print trait will work only for types that also have the display, and provide the functionality that outline print need. We can do that in the trait definition by specifying outline print : display. This technique is similar to adding a trait bound to the trait. So yep, we have to have display like this here. Then we can do all these crazy asterisks. Yeah, because we have specified that outline prints requires the display traits, we can use the toString function that's normally implemented for any types that have the display trait. If we try to use the toString without adding a colon and specifying display trait after the trait name, we get an error saying no method named toString was found. See what happened when we try to implement outline print on a type that doesn't implement the display, for example, point like this, then we have a crap. This is what happened. And then we have an error. To fix this, we'll implement, so we have to have a display trait for point and satisfies the constraint. Using new type patterns to implement external traits on an external types. The often rule that, so this is what it was saying, the new type pattern and stuff. We are getting super confused here. Okay, so new type pattern to implement external traits. mention the other rules that only allowed to implement trait on a type if either the trait of the type are local to our crate. So we want to call in format and then format display. So what's going on here? Yeah, I'm super tired. I want to have a nap, but like kind of after lunch nap, siesta. But still kind of very tired. I'm drinking coffee. It's only my second cup, maybe that's why. The tuple struct will have one field and be a thin wrapper. So what's the difference here? Let's look at this here. It's less confusing if we look at the code. So we have a wrapper struct that have a vector of string. Display for wrapper, we have this. So what do we do? Information of displays use self.0 to access the inner of vec. Because wrapper is a tuple struct and vec t is the item at index 0 in the tuple. Use the functionality of display type on wrapper. So this is a technique we're calling something inside it. No, because string has a display, we're using it or something like that, isn't it? What's going on? Create a new type in the tuple struct. And be a thin wrapper around the type we want to implement a trait for. Then the wrapper type is local to our crate. Then we can implement a trait for the wrapper. No runtime performance penalty. What problem we are solving here? Implement a trait on a type where either the trait or the type are local to our crate. So we can have two displayed for string, but we can create a wrapper for string. So now we have display for this. Implement display on vec t, but vec t already have a display. Yeah, display trait and vec t are defined outside of the crate. But we can make a wrapper struct that holds on to an instance of vec t. Then we can implement display on wrapper and use vec t value. So yeah, it's just like if you want to do that, you have to use a wrapper. So there's no penalty, but you can now implement the trait again on something that's external. But because you wrap it intern like here, then you can also put a trait on it here. Because remember in chapter 10 we said that we can only implement a trait on the type that either the trait or the type are local to ours. So if they are not local, you can't implement that. So display is not local, vec t is not local, so we can't do that. But we can, if we create a wrapper, then we can do it. So we have to apply a thin layer of glue between the two because they are not local. So that's the wrapper here. Okay. So that's what we are doing here for this page. Right. What's the other thing? Downside of using this technique, get wrapper is new type, so it doesn't have the method of the value. Have we implement all the methods again on the wrapper? Treat wrapper exactly like vec_t. If we want a new type to have every method of the inner type have, implementing the deref trait on the wrapper to return the inner type would be a solution. If we don't want the wrapper type to have all the methods, just the method that we want, we can also do that. New type pattern is also useful when traits are not involved. Okay. So we'll talk about that in the advanced types. And oh boy. It's taking me half an hour. This is quite a long and complicated page. Okay. So maybe we don't have time for the final project today. It's fine, we'll do it when we come back. We still have a little bit of time. Advanced type. So Rust type system has some feature that we have so far mentioned but haven't yet discussed. Whoa, okay. We'll start by discussing new type in general, explain why new type are useful, and type aliases. Exclamation type. Dynamic size type. Okay. So new type pattern, the type safety and abstractions. Right. The new type pattern is also useful for tasks beyond those we discussed before, including statically enforcing the values are never confused and indicate a unit of a value. So for example, we have the using new types to indicate a unit. We have millimeters and meters. Struct wrap U32 values in a new type. If we wrote a function with a parameter of type millimeters, we couldn't compile the program that accidentally try to call that function within the type of meters while playing U32. We can also use the new pattern to abstract away some implementation detail of a type. The new type can expose a public API that's different from API of the inner type, which is private. New type can also hide internal implementation. For example, we could provide a people type to wrap a hash map that store a person's ID associated with the name. Code using people would only interact with the public API provided such a method to add name. People would need to know that we assign the ID to name. So creating type synopsis with type aliases. So we are talking about the distance again. So this time we have kilometers. I32. So now aliases kilometers is so now you assign it right. So now unlike millimeters and meters type we create, it's not a separate new type. It's just the same name as I32. So I32 kilometers, you can still add them together because kilometer and I32 are the same type. We can add values of both types and we can pass kilometers value to function that take I32 parameters. However, using this method, we didn't get the type checking benefits that we get from a new type pattern. Mix up kilometers and I32 values somewhere, compiler will not give us an error. The main use case for this type synopsis is to reduce repetition. For example, lengthy type like this box. So if it have the func, and then you have sen, and if it's static lifetime, then writing this lengthy type, it'll be super annoying. What am I reading? Okay, wow, we don't like that. So type analysis thunk will be this thing. yeah, it will be shorter. This code is much easier to read and write. Choosing a meaningful name for type aliases can help communicate your instance as well. Thunk is a word for code to be evaluated at a later time. So it's an appropriate name for a closure that gets stored. This is a closure, actually. Oh. Yeah, new closure. Type analysis are also commonly used with the result type for reducing repetition. Consider the standard I/O method. In standard library, I/O operations often return a result to handle situation when operation failed to work. The library has a error struct that represent all possible errors. Many of the functions will be returning result where E is error. Such this function, the right trait, we would have result error. Yeah. So you see that repeat ... error is repeated a lot. So standard I/O has this type aliases decoration. Yeah. Because this decoration is the standard I/O module, we can use fully codified aliases. This is very from here. So if we replace that, we can just use result. Yeah. Type aliases help in two ways. It makes code easier to write. So this is, we don't care about the error, right? Error just so just error here. Usually the difference is only this like T here, so they're the same. We just, you know, if you see this, you know the error is this standard I/O error. Yeah. Makes code easier to write and give us a consistent interface across all the standard I/O. Because this aliases just another TE result TE, which means that we can use any method that works with it. So special syntax like the question mark operator and the never type that never returns. Rust has a special type named exclamation mark that's known in type theory lingo as the empty type because it has no value. We prefer to call it never type because it stands in place of the return type when a function will never return. Interesting. Yeah, it never returns. Bar will never return. This code reads as the function bar never returns. Functions that return never are called diverging functions. We can't create value for the type exclamation marks, which is never, so bar can never possibly return. But what use is a type you can never create value for. Recorded code. The number guessing game, we produce a bit over here. So match. Okay, error, continue. At the time, we skip over some details in this code. And we discussed that match must return all the type of the same type. So, for example, the following code doesn't work. So if it's error, if you return hello, it won't work. The type of guess in this code would have to be an integer and a string. And Rust requires that guess have only one type. So, what does continue return? How are we allowed to return a U32 from one arm and have another arm that ends with a continue? You might have guessed continue has a exclamation mark with a value. That is when Rust computes the type of guess. It looks at both arms. The former one has U32 and the later have an exclamation mark. Because it never had a value, decided the type is U32. The formal way of describing this behavior is what the expression of type exclamation mark can so it can be anything, but it will have nothing. So it can be any type, but it will have nothing in that type. We allow to end this match on with continue because continue doesn't return a value. Instead, it moves control back to the top of the loop. So in error case, we never assign a value to guess. The never type is useful with the panic macro as well. We record the unwrap function, the recursion t value, to do this. So panic also doesn't have a value because val will be val, which is t. In this code, the same thing happens. Val has the type t, and panic has the type never type. So the result of the overall match expression is t. This could work because panic doesn't produce a value, it ends the program. In the none case, we won't be returning a value, it will just crash. Final example is in a loop. So the loops never ends. So exclamation mark is the value of the expression. However, it wouldn't be true if we include a break, because loop would terminate when it got to the break. Dynamic size type and the sized trait. Rust need to know certain details about its type, such as how much space to allocate for a value of a particular type. These leave one corner of its type system a little confusing at first. The concept of dynamic size type, sometimes referred to as DST or unsized type. This type lets us write code using value whose size we can only know at one time. So we have string, we have two string. This has the problem with little crap there. So okay, this is str, not nstr on its own. So it's a DST. We can't know how long the string is until runtime. We can't create a variable for the type str, nor can we take an argument of type str. So this one won't work because it's str, it's not nstr. Rust need to know how much memory to allocate for the value of a particular type, and all values of type must use the same amount of memories. If Rust allows to write these code, the two-star value would need to take up the same amount of space, but they have different lengths. So S1 12 bytes, S2 15 bytes. Not possible. So what do we do? In this case, you already know the answer. We make the type S1 and S2 an str rather than str. Remember the string slice section, that the slice data structure just store the starting position and the length. So though nt is a single value and stores the memory address of where t is allocated, nstr is two values, the address and the length. Can know the size of an nstr value at compile time is twice the length of use size. That is, we always know the size of an n string. In general, this is the way in which dynamically sized type are used in Rust. They have an extra bit of metadata that stores the size of the dynamic information. The golden rule of dynamic size type is you must always put values of dynamic size type behind a pointer of some kind. But we can combine stir with all kind of pointers, not just nstr. For example, we have box stir, rc stir. In fact, you have seen this before, but we have different dynamic size type traits. Every trait is a dynamic size type that we can refer to by using the name of the trait. We mentioned that to use trait as trait objects, we must put them behind the pointers. Yeah, so that's why we have the box trait, and rc trait would work too, or you just use the good old end. To work with DST, Rust provides a size trait to determine whether or not a type size is known at compile time. This trait is automatically implemented for everything whose size is known at a compile time. In addition, Rust implicitly add a bound on the size to every generic functions. So if we have generic functions, we have this. It's actually treated as this because we need the size. So yeah, it needs a sized trait. Everything needs a sized trait. By default, generic function will work only on types that have a known size at compile time. However, you can use the following special syntax to relax these restrictions. A trait bound on question of size means that t may or may not be sized, and this notation overrides the default that generic type must have a known size at the compile time. The question mark trait syntax with this meaning is only available for size, not for any other trait. So this is special. You can't do this for other traits. Also note that we switched the type of t parameters from t to nt because the type may not be sized. This is not sized, so we can only point to it. Yeah, use it behind some kind of pointers. Right. Then we'll move on to function enclosures. Am I streaming on Twitch? I used to stream on Twitch, but I stopped doing it because I'm lazy. Because Twitch, you have to download the video and put it on YouTube if you want to keep it. Otherwise, it will be gone. I'm not that popular on Twitch, so they won't keep my video for long. So I just do it on YouTube nowadays. It's much easier for me. Yeah, it's mainly for me to keep my record of learning things. I may do more other things in the future, but it's just I love the fact that I put everything in one place. Twitch is fun, but I think it's too complicated for my brain at the moment to do both Twitch and YouTube. So yeah. Okay. Wow, has been a big section here. We have two more. Let's move on. Advanced function enclosures. So function pointers, returning closures. We've talked about how to pass closures to a function. You can also pass regular functions to functions. Okay, this is kind of like how decorator is created, right? This technique is useful when you want to pass a function you have already defined rather than defining a new closure. Functions queries to the type fn with a lowercase f, not to be confused with the capital Fn closure trait. The fn type is called a function pointer. Passing functions with function pointers will allow you to use the function as an argument to another function. The syntax for specifying a parameter of a function pointer is similar to that of a closure. So we have add one here, do it twice, we will pass this inside. So we have a function and then have a value. So we would add them together. So doing it 2 times here. Yeah. The code points to the answer is 12. We specify that the parameter f in do twice is a fn that takes run parameters of type i32 and return i32. So this is the function. Unlike closures, fn is a type rather than a trait, so we specify fn as a parameter type directly, rather than declaring a generic type parameters with one of the fn traits as a trait bound. This is just the type. Function pointers implement all three of the closure traits. We have the capital Fn, Fn mu, Fn ones, meaning you can always pass a function pointer as an argument for a function that expects a closure. It's best to write function using a generic type and one of the closure traits, so your function can accept either function or closures. That said, one example of where you should want to only accept Fn and not closure is when interfacing with external code that doesn't have closures. C functions can accept functions as argument, but C doesn't have closures. That's fair enough. Yeah, for example, we have the list of numbers, list of string, the map. Alright. Or we could name a function as argument to map. So toString, this is toString.collect. Note that we must use the fully qualified syntax we talk about, so we have to do this toString because otherwise we don't know which toString we're calling. Yeah. Okay, so recall from the enum. Value sections. Name of each enum variance that we define also become initializer function. We can use these initializer functions as a function pointer. They implement the closure traits, which means that we can specify the initializer function as an argument for the method. So we have enum status. So status value. This is actually initializer function. Here. We create this status values instance using each U32 value in the range that map is called on by using the initializer function. Some people prefer this style, some people prefer to use closure. They compile the same code, so it doesn't matter. Performance wise, they are the same because after compilation they are the same. But this is just different type of syntax. Returning closures. Closures are represented by traits, which means you can't return closures directly. In most cases where you may want to return a trait, you can instead use the concrete type that implements that trait as a return value of this function. However, you can't do that with closures because they don't have a concrete type that is returnable. You're not allowed to use the function pointer fn as a return type. For example, here, return closure, try to return a closure, and it won't work. So with the closure trait, it will take the I32, so it will take an I32x, but it won't work. Yeah. Ooh, reference the sized traits again. Rust doesn't know how to space it. We need to store the closure. How much space you need to store the closure? It doesn't know. We saw a solution to this problem. We can just use the trait object. So we just make it a pointer. Then it will work. Then we box deal. And then this one is the closure inside. We have a box holding it, and it's fine. Because closure, we don't know how, Rust don't know how big a closure is. So yeah, we have to use a pointer to do that. This code will compile just fine. So it's either using a function, which is like you can use function pointer, or if you want to return a closure, you have to do it with a pointer. This is what's going on now. Okay, so this is this one. We can still move on to the macros and then oops and then wrap up until next time for the final project. Depends on how much time I have this evening. I have a meeting in a bit less than an hour, so let's finish macro and then moved on. Oh, also I have other things to do. I have a deadline tomorrow, so yeah, I may not come back to it depending on how much time I have. Again, how much time I have. Okay. Macros. We've used macros like printline throughout this book, but we haven't fully explored what a macro is and how it works. The term macro refers to a family of features in Rust, decorative macros with macro rules, and 3 kinds of procedure macros. Custom, the hash derivative macros specify code added with the derivative attribute used on the struct and enum. Attribute-like macro that define custom attribute usable on any item. Function-like macro that looks like a function call but operates on a token based on their arguments. So, why we even need macros when we already have functions? The differences between macros and functions. This is what I have in my mind a lot. Fundamentally, macro are a way of writing code that writes other code, which is known as metaprogramming. In Appendix C, we discussed the derived attribute, which generates an interpretation of various traits for you. We also used the printline and vec macros throughout the book. All of these macros expand to produce more code than the code you have written manually. Metaprogramming is useful for reducing the amount of code you have to write and maintain, which is also one of the role of the function. However, macros have some additional power that functions don't. A function's signature must declare the number and type of parameters the function has. Macro, on the other hand, can take a variable number of parameters. We can call print like hello with an argument, or print like hello and name with 2 arguments. Also, macros are expanded before the compiler interprets the meaning of the code. So, a macro can, for example, implement a trait on a given type. A function can't because it gets calls at runtime, and a trait needs to be implemented at compile time. The downside to implement a macro instead of a function is that macro definitions are more complex than function definition because you are writing Rust code that writes Rust code. Due to this indirection, macros definitions are generally more difficult to read, understand, and maintain than function definitions. Another important difference between macro and functions is that you must define macros or bring them into the scope before you call them in a file. As opposed to functions, you can define anywhere and call anywhere. There are decorative macros with macro rules for general metaprogramming. The most widely used form of macro in Rust are decorative macros. These are also sometimes referred to macros by example, macro rules, exclamation mark macro, or just plain macros. At their core, decorative macros allow you to write something similar to Rust match expressions. Macro also compare value to the pattern associated with particular code. Right, let's see how it works. To define the macro, you use the macro rule construct. Let's explore how to use macro rules by looking at how vec macro is defined. So vec has 3 integers, so what's going on here? Use the vec macro to make a vector of 2 integers or a vector of 5 string slices. We wouldn't be able to use a function to do the same because we wouldn't know the number of type of value up front. So this is how the vec macro got defined. Macro export, that is add another file. Macro is vec. The there are lots of the dollar sign here, and then this is familiar. This is Rust code. Okay, what's going on here? The actual definition of web macro in the standard library includes code to pre-allocate the correct amount of memory upfront. This code is optimization that we don't include here to make it more similar. So this is not the real implementation. This is the simplified version. So macro export annotates this macro should be made available whenever the crate in which macro is defined is brought into scope. Without this annotation, macro can't be brought into scope. Start the definition with macro rules. Followed by the curly bracket. So this is the body. Similar to the structure of match expression, we have arm with pattern followed by this. But what is this? Block of code associated with this pattern. If the pattern matches, the associated block of code will be emitted. Given that this is only pattern in this macro, there's only one better way to match. Any other pattern will result with an error. More complex macro, we have more than one arms. Where the pattern syntax in macro definition is different than the pattern syntax covered in chapter 18 because macro patterns are matched against Rust code structure rather than values. So you can look at Rust reference to see how to do the macro pattern syntax. Set of parentheses to compass the whole. So $sign to declare a variable in the macro system that will contain the Rust code matching that pattern. The $sign makes it clear that it's a macro variable as opposed to a regular Rust variable. Next comes a set of parentheses that capture the value that matches the pattern within the parentheses for use in replacement code. This matches any Rust expressions and gives the expressions to the name X. The comma following indicate that it's a literal comma separator. So the first variable will be here. So this will be X because this one matches. So comma is comma here. So this one matches the one here, right? The star specifies the pattern matches 0 or more wherever the proceeds the star. Matches 3 times within 3 expressions. So it's generated for each path that matches the pattern 0 or more times. Depending on how many times the pattern matches. So the $x is replaced with each expression matched. So this will become this. So because this one will capture 1, 2, and 3 each time, so this one will become so 1, 2, and 3. So this will be 3 times. And then this is the repeat. So yeah. Then this is the end. So return the 10 vex. We have defined a macro that takes any number of arguments of any type and can generate code to create a vector containing the specified elements. So this is the vec macro does. What the vec macro does, simplified version. Okay, procedural macros will generate a code with attributes. Oh yeah, there's another book about macros as well. If you want to read it, maybe read it in the future when we have time. But not anytime soon. I think we should be more familiar with how Rust works before we dive into the Rust macros. Generating code with attributes. Second form of macro is procedural macro, which acts more like a function. type of procedural macro, accept some code as input, operate on that code, and produce some code as an output, rather than matching against pattern and replace the code with another code, like decorative macro does. 3 kinds of procedural macro are custom, deriv, attribute-like, and function-like. Work in similar fashion. We create procedural macros. The definition must reside in their own crate with a special crate type. Complex technical reason. Okay, we'll see. In the list, sorry, I'm making noises. I'm stepping on a paper box. So now it's like I've compressed it too much. Let me release it. Okay, sorry about that, the noise. In list 19 to 29, we show how to define a procedural macro where some attribute is a placeholder for use a specific macro. So, use procedural macro. Some attribute. This looks familiar. Props function name. Okay, so what's going on here? The function that defines the procedural macro takes a token stream as an input and a procedure token stream as an output. The token stream type is defined by procedural macro crate that is included with Rust and represent a sequence of tokens. We have multiple kinds of procedural macros in the same crate. Yeah, so this looks like the derive. So what's going on here? Create a crate named hello macro that defines the trait names hello macro with one associated function named hello macro. Rather than making our user implement the hello macro trait for each of the type, we'll provide a procedural macro so users can annotate the type with a hash. Derive hello macro to get a default implementation of hello macro function. The default implementation will print hello macro, my name is type name, my type name is name of the type. We will write a crate that assemble another program to write code. Use hello macro derived, hello macro. Struct pancake. So pancake will have hello macro. So this code will print hello macro, my name is pancake. When it's done, the first step is to make a new library crate like this. So in the library, we'll have the hello macro. It will have a function, hello macro. So we have a trait and a function. Our crate user could implement the traits to achieve the desired functionality, like so. Struct pancake, you can have impel hello macro for pancakes, and hello macro could print that. However, they would need to write the implementation block for each type they want to use hello macro. I'm going to spare them from doing that. So you can yet provide a hello macro function with default implementation that will print the name of the type of the trait implemented on. Rust doesn't have reflection capability, so it can't look up the type name at runtime. So that's why we need to use a macro to do that. Next step is to define the procedural macro. Need to be in their own crate. Eventually these restrictions may be lifted. The convention for constructing crate and macro crate is as follows. For crate name foo, a custom derived procedural macro crate is called foo derived. Just add derived at the end. So it is called hello macro derived. Yeah. So they need to be separate for now. Our two crates are tightly related, so we create a procedural macro crate within the directory of our hello macro crate. If we change the trait definition, you have to change the implementation of the procedural macro as well. The two crates will need to be published separately, and the programmer using these crates will need to add both as dependencies and bring them both into scope. We could instead have the hello macro crate use hello macro derive as a dependency and re-export the procedural macro code. However, the way we have constructed the project make it possible for programmers to use hello macro even if they don't want to use the derive functionality. We need to declare the hello macro derive crate as a procedural macro crate. We also need to functionally from the scene and quote crate. You'll see in a moment. We need to add them as dependency, so we need scene and quote. Here we also have to do pro macro equals to true. To start defining the procedural macro, place the code in there. Yeah, it won't compile yet. So procedural macro token stream. Procedural macro derive hello macro. Hello macro derived input token stream, output token stream. Then we will construct a representation of Rust code to do that. The ASTU equals to scene pass input to unwrap. Then input hello macro. So we have split the code into hello macro derived function responsible for parsing the token stream and the input hello macro function here, which is responsible for transforming the syntax tree. This makes writing a procedural macro more convenient. The code in the outer function hello macro derive, this case will be the same for almost every procedural macro crate you see or create. We have introduced 3 new crate procedural macro, synth and quote. The procedural macro crate come with Rust, so you didn't need to add that to the dependencies. It's the compiler API that allows us to read and manipulate Rust code within our code. Scene crate passes Rust code from a string into a data structure that we can perform operation. Quote returns in data structure back to Rust code, so they come in hand. This crate make it much simpler to parse any sort of Rust code we may want to handle. Writing a full parser for Rust code is no simple task. The hello macro derive function will be called when a user of a library specified a hash derive hello macro on a type. This is possible because we have annotated the hello macro derive function here with the procedural macro derive and specify the name hello macro, which matches our trait name. This is a convention most procedural macros follow. The hello macro derive function first convert the input from a token stream into a data structure that we can interpret and perform operation on. That's where synth come into play. And the parse function in synth take a token stream and then return the derive input struct, representing the parsed Rust code. So again, from the struct pancake, we'll have this. Indent is an identifier, pancake. We'll define the input hello macro function, which where we build the new Rust code we want to include. But before we do so, notice that the output for a derived macro is also a token stream. The return token stream is added to the code that our crate user write. So when they compile the crate, they will get extra functionality that we provide in the modified token stream. I'll call it unwrap to cause the hello. I have half an hour. Oh my god, okay. Unwrap to cause the hello macro derived function to panic if the call to the same pass function fails. Necessary for our procedure macro to panic on error because they must return the token stream rather than result. To conform to the procedural macro API. So you just use unwrap. So if anything goes wrong, you just died. You provide more specific error message by writing panic or expect. But now we have a code to return the annotated Rust code from a token stream into a derived input. So impel hello macro. So we'll take the derived stream that's generated from Syn, so the AST actually. So we'll do something about it. So AST, so that's the name, intent, and then generate. So this code will get the gen back. So gen into would give it back as a token stream. So impel macro for name will be the name here. And then from hello macro, my name is, so name again is name stringified. So macro within a macro, hello. Macro with this is no, actually this will be become the token stream, right? So this is not actually putting the macro here. So this macro will become another macro, and it is funny. Okay. But yeah, anyway, so we turn the token stream using synth into AST, and then the AST, now you can write some code, because what we need from this AST is the name of the instance, which we have. And I write some code, and then put it back into, using quotes to make it back to the token stream. Right, the quote macro. Let us define the Rust code that we want to return. The quote macro also provides some very cool templating mechanism. We can use hash name, replace it with the value of the variable name. Do some repetition similar the way regular macro works. Yeah, there's more stuff we can dig into. I think I would revisit this when we look at macro in more detail, but we don't have time for now, and we don't want to overload ourselves. Remember, we are Rust babies, so we don't know how to do this yet. So yeah, let's not dive too deep into macros. Okay, stringify macro, of course, built in Rust, so it will make it into a string. So pancake will be a string. Okay, at this point, cargo build should complete successfully. So let's put this crate into the code that we're using them. So path equals to this. Okay. Now you should be able to use it. Yeah, let's not dive too deep into it, but we kind of generally got the idea how it's done. So attribute like macros. Similar to custom derived macros, but instead of generating code for derived, create new attributes. More flexible, derived only work for struct and enum. Attribute can be applied to other items as well. So attribute name route that you can annotate function using web application framework like that. Yeah, there are also macros like that in Pio3, I do believe. When we started looking at Pio3, we know what's going on. Kind of a brief idea what's going on. Yeah, I'm not going to dive into this. Similar idea. Function-like macros. Function-like macros define macros that looks like function calls. Similar to macro rules macros, they are more flexible than functions. For example, they can take an unknown number of arguments. However, macro rules macro can be defined only using the match-like syntax. Function-like macros take a token stream parameters, and the definition manipulates the token stream using Rust code, as the other two types of procedural macros do. So for example, SQL macro. So take a token stream and give back a token stream. So, some Rust feature in your toolbox that you likely won't use often, so we will come back when we need to use them, but you will know they're available. Introduce several complex topics. You encounter them in error message suggestions. Okay. So next time, we'll do the project. We'll do the final projects. Let's have a quick look. Quite scary. Oh, actually, first page is your introduction. This is. It reminds me of the Django getting started tutorial. is quite long, but I think we should do that within 2 hours for sure. We just follow them and create the things. Wow, it's quite long. Yeah, but it should be within 2 hours. Okay, next time we'll do this. But for now, so there's a lot of things to learn. Like in the future, macros is one thing, but I don't want to start it. So let's do this, and then we'll do the Rusting exercise, and then we'll find some baby-friendly Rust project to work on. Some fun stuff, and then yeah, and then like in the future we can go back to look at macro. We can also look at Pio3, which is another fun thing to do. So yeah, there's a lot of things to mess with Rust, which I think is quite fun. So yeah, so goodbye for now. I have to prepare for the meeting, and I will see you all later today, or when I come back from Berlin, which is next week. So either later today or next week. Sorry about the spying schedule of Rust. When I'm traveling, I'm super busy, but let's see if I can bring my second monitor. I'm buying a second monitor, hopefully, because like it's very difficult to stream, because at home I have another monitor. I can look at how the stream look like, but and also like kind of the control and everything. But if I am away, there's like no way I'm gonna do. So hopefully 2 screen will help, and the quality may be different. I don't have a good mic, I don't have a good lighting, I don't have a good camera, but maybe it's doable. So so for now, goodbye, and then see you next time.